Okay, welcome everyone to the ICTS seminar by Darshan Joshi, who was our colloquium speaker yesterday. For those of you who were not in yesterday's colloquium, I'll briefly introduce Darshan again. So Darshan currently is at Harvard working as a postdoc in Professor Subhi Sachdev's group. He started off as an undergraduate student at IISER Pune, and then he did his PhD from TU Dresden with Professor Matthias Weiter, and then he spent 2 or 3 years at Max Planck Institute for Solid State Research in Stuttgart. And as I said, he's now at Harvard. And his research interests broadly lie in quantum phases and quantum phase transitions in strongly correlated systems, frustrated magnets, and similar systems. Yesterday, he told us, he gave us a very nice overview of certain non-Fermi-Liquid type phases in some strongly correlated systems. And I believe today he's going to tell us in some more detail about something called critical non-Fermi-Liquid metal in an overdoped random TJ model. Okay, so Darshan, please start.
Yeah, thank you, Sthitadi, again for the nice introduction and for everyone joining live as well as on Zoom for this talk. So today I will be talking about a particular non-Fermi-Liquid phase in the model that I briefly talked about yesterday in the colloquium. And this work has been motivated by certain recent experiments again, and also our continued interest in these random and all-to-all models. So just to again get everyone on the same page, continuing from yesterday's discussion, I showed you this phase diagram for the cuprate physics, which is a complicated high TC superconducting material with lots of phases. But in the end, we saw that recent evidence and observations suggest that there are some fundamental questions that you can ask, and this is one of the things that we discussed yesterday, that could we have a quantum phase transition as a function of doping between some metallic phase at low doping with some spin glass order, presumably, and some Fermi-Liquid-like phase at high doping. And we looked at this quantum critical point using renormalization group theory with, and considering a particular random model, which was this random TJ model, where we started with a SY model, which was a Mott insulator with random exchange, and then we doped it. So today, so yesterday we just looked at the quantum critical point. I did not really talk about any of the individual phases. So this was basically why we did renormalization group. So the renormalization group just told you that there is a quantum critical point and it separates some two phases. So now our interest is in looking actually in detail what are these phases at low doping and high doping. And in doing so, I will be taking a completely complementary approach. So of course, I cannot use my renormalization group anymore. So I will be using enlarging my symmetry and solving this model and looking at the solutions of the model that I described yesterday. But there's actually an interesting twist to this story in recent times that let me just mention to you briefly before I go into the details of solving this model. And this new observation is that as you can see from the schematic phase diagram, at high doping, you expect that everything is basically a Fermi-Liquid metal, and even like experimentalists and many of the people in the community did not pay much attention to this overdoped region or high doping region of cuprates, presuming that it's just an ordinary metal. But interestingly, recent experiments, what they have found is that even in this overdoped region for a considerably large doping domain, like almost 10%, you still find strange metal type of anomalous transport signature. So unfortunately, you probably do not see some color shading here. So let me just walk you through. So this is precisely like the schematic phase diagram that I showed you on previous slides. So the y-axis is temperature, x-axis is whole doping. This P star kind of thing is exactly what I showed you before, that there is some phase transition between low doping and high doping phase. What is shown here is this shaded region. So it was presumed that this strange metal basically emerges from this P star point and that's it. It's like a fan-like structure. But now people have observed that even to significant higher doping, you find some anomalous transport, just like T-linear behavior that I talked about yesterday. So this is what is shown in this phase diagram schematically, and these are the observations or the coefficient of this linear in temperature resistivity term. So this y-axis is the coefficient, x-axis is the doping, and what is shown here is that this coefficient of this linear term essentially vanishes around this point, and then you have a Fermi-Liquid behavior. So then the upshot now is that you have this quantum critical point around this P star, but then your system from this, when you come from the low doping side, it doesn't immediately go into a Fermi-Liquid phase, but there is some non-Fermi-Liquid phase window in a broad range of doping. And this is what now I will talk about, and I will present a candidate non-Fermi-Liquid that could describe this phase which is presumably there.
Darshan, a quick question. What is the reference for this?
Oh, you don't see the reference? I'm sorry. I did put it, but it's not visible. So it's a paper by Nigel Hussey, and I can just write it on the blackboard.
Okay, got it. Yeah.
Sorry about that. So it's somehow cut out. Yeah. So let me then go to the blackboard and work out the Kijé model now. Yeah, so the first figure is basically a schematic phase diagram that they drew. So here, these data points, these blue and green things are the points where they actually did the measurements. So they are just showing that in this is the region where they did their measurements for two or three different samples. And in this right plot is actual data of your coefficient of the T-linear resistivity. Okay. Okay, so let me just write down the reference of this previous observation. Is it visible to everyone? Okay. Is it visible now, or should I write bigger on the Zoom?
No, it's good. It's good.
It's fine. It's visible.
Okay, thanks. So this is the reference for this experiment. Okay. So let me then begin with the model that I was playing around with yesterday. So this is the random Kijé model. So the Hamiltonian was basically you had a hopping term, and again this is all to all. So you have n sites, which is not a lattice, but they are connected to each other, and you have electrons hopping between site I and site J, and you have a random exchange interaction, which is again all to all with a exchange interaction Jij between the spins at site I, site J. And of course, there's a chemical potential on every side. And these Tij, Jij are random numbers with mean value 0 and mean square value of T square and J square. Okay, so now today we are going to solve this model and try to look at the solutions of this problem. So yesterday we solved this model for the SU2 symmetry. So of course, doing this now analytically and finding the solution of this model for SU2 is not easy doing this analytically, but you can find solutions, low energy solutions to this problem if you enlarge your symmetry to a larger one. So what essentially we will do is enlarge your SU2 symmetry to SUM for the spins. And in general, as I said yesterday, you have this SU12 algebra because we fractionalized our electron into a holon and a spin-on. So if you recall, Ci alpha was Fi alpha, Bi dagger. So this was the holon, this was the spin-on, and you could also write the spin operator on every side in terms of the spin-ons. So there was just one species of boson and two flavors of fermions. So this was the SU12 algebra. And now we are going to enlarge this symmetry and this superalgebra to SU m prime dash m. So this would mean that we introduce another label to the bosons. So we also promote the number of flavors of bosons. And let's label it with L. So here there would be another index L. And there is alpha. So now L goes from 1 to some number m prime, and alpha goes from 1 to m. So this is an enlarged symmetry problem. And just like any large symmetry calculation, large M calculation, the spirit of this calculation is that we will be working in the limit of large M prime and M, such that the ratio of M prime and M is finite. So you take the limit of M prime and M to be infinity, keeping the ratio to be constant. So that's the spirit of the setup. Yeah, that's still there. Right. So this is the basic setup. And now in terms of this, you can write your action, which is basically writing now in the large M spirit. So this is the free boson piece. And analogously, there is a free fermion piece. So this lambda is corresponding to your constraint because you have now partitioned your electron into holon and boson. So remember when we were working in this SU12 superalgebra, we had the constraint that B dagger B plus F dagger F is 1. So here in this case now, it's basically BL dagger BL and that's the M/2 coming up there. And then you have the usual pieces coming from the interaction. So the hopping term, that's the T square. And again, recall that there were these self-consistency fields that we dealt with yesterday, that you had to impose a self-consistency condition. So these are the self-consistency fields. Right. So this is the action that we want to basically deal with. And from going from here to here, I have done exactly the same thing that I did yesterday. You do disorder averaging. So first you enlarge the symmetry, of course. Then you do the disorder averaging such that after taking the limit, m goes to infinity. Now this n is your number of sites. So that's taking the thermodynamic limit. You arrive at an effective single site action. So this is the action now that would be the center focus of our finding the solutions. So this is what we will be working with. And now the idea is that we look at this action and now we want to solve it. And first step is to actually look at the saddle point equations of this. So you just extremize this and look at what are the saddle point values, saddle point equations. And of course, recall that again, let me stress that these R and Q fields have to be self-consistently determined, and these are related. So R is related to the electron correlator, and Q is related to the spin-spin correlator.
How does the M counting work in the
This one? Yeah, this one, you mean?
Yeah, so
yeah, you have to scale the, when you do the enlargement of your symmetry, you also have to scale your coupling constant with 1 over m, the coupling constant.
why is there no m square root?
M here
Okay,
as well.
okay.
Thanks for pointing that out. Yeah, so you have to scale both of them
now
with
it
1
makes
over
sense.
m correctly. Thanks. Yeah, so now this is what we will be solving. So let me just write down the saddle point equations directly here. So you have the boson and the fermion particles that we want to solve. So of course, sorry? Sorry? Yeah. So we have already performed the disorder averaging in arriving at this action.
So you are averaging the action or averaging the exponential of the action?
Exponential, of course, yeah. So we are averaging log z in.
Okay.
Yeah. So basically going through the whole step of introducing replicas and then doing the disorder average and all that stuff. So I'm skipping that part. And here I'm just keeping replica diagonal terms in my action. Because so at some point when we will talk about the spin glass phase, we also have to worry about the replica of diagonal terms. But for this particular problem, for this particular phase where we are interested in, it is replica diagonal, essentially. So that's why it's a bit more simpler. Yeah, but we go through all that jugglery of averaging over log z and taking n goes to 0 limit and so on. So then the saddle point equations. So this is G inverse of A. And here A stands for either fermion or boson. And sigma of the self-energy of the fermionic particle now looks like minus J square, G square F of tau, GF of minus tau. And of course, there's also a relation that relates your Green's function to the doping. Okay, so these are the principal equations that I'm going to solve. So like looking at the self-energy expressions, you can easily see how you get it. So for instance, if I want to look at the fermionic self-energy, just look at this term. So this is the term that is proportional to T square. So there is a term proportional to GB, that's the Green's function of the boson, and proportional to R, which is the correlator of your electron Green's function. And the electron Green's function is a product of your fermion Green's function and the boson Green's function. And that's why this T square term has 2 GBs and 1 GF. And if you look at the contribution from J square, then essentially you only have GFs. There is no GB involved in that. Yeah, K is the ratio of M prime over M. And similarly, now you can also easily see what's the self-energy for the bosons. So self-energy of the bosons comes from only this piece. and that is proportional to the the Green's function GF, and R, which is again proportional to GF times GB. So then you have two GFs and one GF GB. So that's essentially the problem or the set of equations that we are going to solve now. And yeah, so we will look at the solutions of these equations, essentially.
That's the doping, and that's sort of, you put that in as the
Yeah, P is the doping. Yes, that's right. Yeah, yeah. So P is nothing but the boson density. Yeah. Yeah. In other words, I'm just expressed in this. Yes, correct. Okay.
Sorry, so this is some large M prime.
Yes.
And you're keeping M prime by M fixed. Is
Yes,
that
the ratio of M prime over M fixed? Yes.
so? And you're taking the limit M prime and M being large.
Right. Exactly.
Okay.
Yeah. And this is where the theory is controlled, and we can actually look at the saddle point equation. So of course you can go beyond this and ask the question, what are the 1 over M corrections and so on, but I won't be talking about that today. I will briefly mention something related to it, but we won't really go into the calculation of this. Okay, so then now our task is to solve this set of equations, and it turns out we basically use the wisdom that you gain from solving the SY solution, so the Sachdev-Ye model or Sachdev-Ye-Kitaev model. And the wisdom is that you would find some gapless solution to this set of equations. And one way to see that is your G. So suppose you make an ansatz like this. So I think I can erase the action. Now I don't need it. So let me just run you through the logic that Sachdev and Ye used when they solved this set of equations. So assume that your Green's function Gz is some power law in Z. Then you can argue that if you now look at the imaginary part of this Green's function and suppose it is gapped below a certain value delta, then if you look at the self-energy, it's cubic in your Green's function. So that would imply that the imaginary part of your self-energy would have a gap which is 3 times your gap that you presumed to be in your system. And if you now put back in your Green's function, because your Green's function depends on self-energy, and because you have some power law mu, this first term is basically irrelevant. This cancels with the 0th order, and this term essentially tells you that your G is proportional to sigma, and sigma is cubic in G. And then using that logic, you essentially arrive at the fact that there is only one possible solution where your gap is 0. So you start with the solution that is gapless, and this set of equations, they all allow only gapless solution, and that's actually a remarkable beauty of these equations, because let's say finding a gapless fermionic solution is not that difficult, and it's probably a trivial statement that one may say, but actually finding a stable gapless bosonic solution, that's something extremely non-trivial, because usually the bosons have the tendency that as soon as the gap closes, they condense. So this is one of the very rare example where bosons actually have 0 gap and they remain critical in some finite parameter space. So that I find like very exciting about this model, that the bosons can remain critical gapless. So now let's try to solve this problem. So to solve this problem, again, let's we make an ansatz, and the ansatz is as follows. So let me just write it, and then let me motivate what different terms are. So this is written in the upper half of your imaginary plane. So Z is a complex frequency, a complex number. So you now have, of course, working with Matsubara frequencies, I omega, and you write down your Green's function in the entire upper half plane. And yeah.
Is there a restriction of what a k can be?
K? No, it can be any finite number.
Half minus k being negative, positive, and
You mean from here?
yeah.
Yeah, so as long as, so for a given k, you can ask the question the other way around. For a given k, can you find a meaningful solution that satisfies all the saddle point equations, including the condition that the doping value that you get from the Green's function for fermion and boson is the same. So you can just invert the question and ask that. And if you don't find a meaningful solution for a given value of k, then yeah, you just conclude that for that particular value of k, there is no solution. Condensation of bosons? Yes, so strictly speaking, it's controlled in the large M spirit, but you can also show that even if you have 1 over M corrections, the boson still remains gapless. Yes. So this is really the low energy property is fully captured by these saddle point equations. And this is in the spirit of any systematic expansions that you do, that the one that you get at the saddle point is usually your good starting point, and your corrections does not destroy it. Because if the corrections destroy it, then yeah, then this is really not a good theory. But here you can see that the corrections don't destroy your saddle point solution, and they remain gapless. Yeah, there have been like very interesting works where people have, so for instance, this type of solution, which I will just describe in a moment, people have looked at it, and then they have also looked at, so this is what people call, or you can see that it has a conformal form and it has a conformal invariance, and it's in the low energy sector. So this is not a solution which is like valid everywhere in your frequency space, but this solution describes your low frequency piece. And of course, there are like finite corrections coming from high energy contributions. But what people have also studied is if you perturb your system slightly such that you break your conformal symmetry and introduce certain operators, what happens? And this has also been well studied. And that sometimes actually becomes important in certain aspects of like conductivity or resistivity.
Can I ask a question?
Yeah.
I have a question actually.
Yeah,
So in the standard SYK model, one discovers the low energy effective degrees of freedom. So do you have some similar discussion over here?
You mean like some soft mode? Or...
Exactly, the soft mode there, which satisfies the Schwarzschild equations of motion. So there should be something similar here, maybe a little bit more complicated.
Yeah, so there is definitely this time reparameterization symmetry that gives rise to soft mode in your pure SYK model, and that is actually also true for these type of solutions. But what's exactly the nature of these soft modes, like how you would write it in terms of some at the level of operators, I'm not sure. I think it's a slightly complicated thing.
Yeah, no, that was not my question actually. I mean, that one has to compute the 4-point function and sort of derive those things like Stanford and Maldacena did.
Right.
But would you say that the low energy mode is simply the reparameterization of time mode, and the effective action at low energies is still the Schwarzschild? I mean, it's okay, you don't know how to compute the coefficient of the Schwarzschild, it's very complicated. I admit that, but is it just the Schwarzschild then?
Yeah, that's true. That is correct, and I agree with that. That is definitely true for this system.
Okay.
Yes.
Thank you.
I think in some context, people have written actually the Schwarzian and everything for this random TJ model. So it's definitely true. Yes.
Thank you.
Just to clarify, so it's a Schwarzian with this, with some symmetries, some bosons. Now you have bosons and fermions. And,
yeah, you have both. Yeah.
And but there's only Schwarzian at low energies, at low frequencies.
Yeah. You can write it in the Schwarzian form. Yes. I don't remember or what exactly is the form, but I'm aware that you can write it. Yes.
Okay. What is the? I guess you'd probably be saying, what are the low frequency modes in the system? All of them are.
Yeah, these are basically the bosons and the spinons and holons. So these are the physical modes in our system.
And how are they related to this time reparameterization modes?
To the time reparameterization soft mode, that I don't exactly know the form. Yeah.
Okay.
yeah, if I think more, probably I can recollect, but I cannot remember at the top of my head. Yes.
Of this has a branch cut?
Yes, precisely. Yes, yes. And this branch cut is very important because that's what actually tells you that there are no long-lived quasi-particles. It's not a simple pole, but it's a branch cut. Yes. And that's actually very important that you have this ansatz with a branch cut.
Operationally, do you choose a k for your calculations, or you just do things in terms of k?
Yeah, so most of the things, like getting down to certain level where you, let's say, find out what the coefficient is in front of this low frequency ansatz, what is the value of delta, like the exponent and so on. For like particular choices of solutions, you can actually work them out analytically, or at least you can work out a closed form relation between these different parameters, independent of like choosing k. So you can write everything in terms of k. But when we, of course, solve it numerically, let's say at finite temperature or zero temperature, then we make, of course, a particular choice of k. But you can do it for different values of k. Yeah. Okay. But so at the end, I would be, of course, making a very heuristic approximation by saying that I'm interested in k equals 1/2 because that's the physical case where m prime is 1 and m equals 2. So some of the plots, for instance, that I will calculate numerically, those will be for k equals 1/2. But we also looked at certain expressions, how they behave as a function of different values of k for large m and so on. Yeah. But a priori, to solve it, you don't need to fix k. Okay, so as you pointed out, this is the important part, that there is a branch cut in your ansatz. So this basically tells you that there are no long-lived quasi-particles. And so this delta is the exponent that parameterizes this. Then the c is basically a constant, and this theta is the parameter which tells you the spectral asymmetry. So you can either have particle-hole symmetry or particle-hole asymmetry. And we just want to give it more freedom and let it also have solutions which could be particle-hole asymmetric. And this is basically taken care of with this parameter theta a. Of course, there are some bounds on this theta because it has some relations with other parameters that I will come to in a moment.
Sorry, I should have probably asked, what determines k? I mean, we started with some number of fermions, right, some Cs, and then you wrote down an ansatz, some fractionation ansatz. But how do you change k? Like, what is the physics of what determines k?
Yeah, so that's a good question. So that depends on what level of symmetry you want to go to, right? Because k is really just some number that's fixed by the ratio of m prime over m. And you could ask, like, the physical case that we would be interested is m prime is 1 and m equals 2, but you could also do, you could also have a k where you fix m prime to be 1, but take some very large value of m. That's totally depends on at what level of calculation you are interested in, or what value of k you want.
But in the basic model that you started with, there was no k.
There is no particular bound or any choice of k that is restricted to.
So if I just, if that is the model, it will show something in the experiment. So what is the k it will choose?
For the experiment, like 1/2, because that's the experimentally relevant thing. Yes.
Okay. Okay, but how would you realize experimentally other case?
I have no idea. I mean, there are particles which emergent particles, again, that's the beauty of condensed matter, in certain critical phases or certain some strongly correlated setups, you do have like emergent SU3 symmetry or emergent symmetries. Like people, Shubhro is working on different aspects of like some systems where you have larger symmetries. And you could have, some experimental setups where you have some enlarged symmetries. But I cannot give you like a pinpoint example right now where you have a particular choice.
Okay.
Yeah. Yeah, but those are all emergent particles. Okay, so this is the ansatz that we start with. Again, A is for F and B, and I've just written in a general notation. And now to make it slightly more clearer, let's write it down in the imaginary.
Sorry,
time.
if I may, is it something to do with the filling or something?
A filling of what?
Like, for example, like in one context, I'm familiar with, let's say, in fractional quantum Hall effect, where you have many emergent particles and so on.
Yeah.
You get different kind of, phases and different kind of, let's say, effective emergent gauge theories,
Right.
depending on the filling,
Yes.
Landau level and how much fill. So is that the kind of thing that you have in mind, or?
Not here, no. This is even more elementary. You just have taken this large M prime limit and then have this ratio and then work with it. But the physical case in our case is still k equals 1/2. Any other k doesn't have any physical meaning in this model, random TJ model. Yeah.
Okay.
So let's write down in the imaginary time. It's just more convenient to see certain things. So this then becomes, bear with me for a moment.
Sorry, but what if you had the particles with higher spins?
Sorry?
But you could have had particles with higher spins.
Yeah, you can, exactly. But I'm saying that the model that I'm interested in, or this random TJ model that I wrote, that's for electrons, and this is like SU2. But of course, you can have emergent particles in some other system where you can have like higher symmetries, definitely. Yeah.
Yeah. No, you started with this Hello? You started with this action where you have this t square by m and you have j square by m prime or something. And in the saddle point equation, how do you get this ratio m prime by m, and how does k appear?
Here.
But you don't get here.
Yeah, so they're basically your Green's functions. They also have some factors of 1/m, 1/m prime, and they basically give you this ratio of k, like m prime over m. So you remember the action it also had a summation over L and alpha and so on. So you generate some factors.
So you are doing perturbation in 1/n and 1/m prime. And
yeah, but there were also like these summations over alpha and L index. So when you write it for fermions, of course, you write it for a particular flavor alpha, but then there's also a sum over L that comes about, and that gives you a factor of m prime. And whereas for the bosons, you sum, there were only fermionic particles, and the summation was only like over m. So m cancels with m, and that goes away.
Yeah. So I guess, finally you sort of expect that the final answer just depends on the ratio.
Right.
And but to do the calculation, you need large n and large m prime.
I mean, it's just a matter of like doing it systematically as a matter of principle, because if you do it like for finite m or m prime, that would be a very bad Hartree-Fock kind of approximation. It won't be controlled. Then you wouldn't know how to improve on that systematically. Whereas when you enlarge your symmetry and do this saddle point approximation in this large m prime limit, then in principle, in theory, you know how to improve this result systematically in an expansion in 1/m. So that's the whole reason why we do this, enlarging the symmetry. Yeah, it's just a matter of principle to do it systematically.
Thanks. Darshan, can I just ask a question?
Yeah.
This is on Zoom. Yeah. So if I put k equal to 0, just formally in your equations, I notice that I get the SYK part back. Right, and then the sigma b, I suppose I should take GB equal to 0 because, and then that becomes a trivial equation.
Yeah, but
so
you don't
this
have
goes.
Sorry, complete. Yeah.
Yeah, go ahead.
No. Complete your question. Sorry to interrupt.
No, I was just going to say that then K does look like something like filling, right? Because it's like because K does look like filling, right? Because you look at your Green's function at 0 minus, GF 0 minus. So it's 1 minus. If I put K equal to 0, then it does look like half, which is half filled. And then I just get the standard SYK sort of thing, right?
Yeah, but the point is that if you put just k equals 0, that is not enough, right? You also have to put always GB to 0. So the correct thing to do to ask like what's the limit where you get SY physics in this is really like putting GB to 0. So you even if you keep k to be finite and put GB to 0, then essentially you go to
yes,
the SY. So you just put GB to 0 and P to 0. So 0 doping, and there are no like holons anymore, just spin-ons. So that's the correct way to take the limit to the SY.
Okay.
Yeah. So essentially at 0 doping, they are just spin-on degrees of freedom. Or you can also take T to 0 and so on. Okay, probably I'd maybe rush through this now. So this is the time representation in the imaginary time. Okay, so now we have the answers.
Sorry, if I may.
Yeah.
So this G is the Fourier transform of the G in the previous line.
Yeah.
Okay.
Fourier transform of I omega. Yeah. So
Okay.
tau is imaginary time. Yes.
So the GA of Z you've written is in the frequency domain.
Yes.
Okay.
Yeah. I mean, I could have skipped this. I thought that I would need this, but maybe I can skip through many of these details. But the important point now I want to make is that we want to solve these answers. So by just writing these answers, I haven't really solved the problem. I've just made this guess based on the wisdom that it has to be some gapless things with some branch cut. But I actually have to put this G back into this saddle point equation and solve everything consistently, right? So apart from doing this, there is also a constraint that comes from your connection between UV and IR physics. So these are the Latinger relations. So as you know, for normal Fermi-Liquid, in a Fermi-Liquid theory, if you have a well-defined, when you have a well-defined Fermi surface, let's say, for example, a sphere, a circle, then you know that the Latinger theorem tells you that the area or volume enclosed by your Fermi surface gives you the number of electrons or the density of your charges, right? So here you have a similar relation. So if you think about what really the Latinger relation is telling you is it's actually connecting your high energy degrees of freedom to low energy degrees of freedom. It's telling you something about your Fermi surface, which is a low energy property of your system, and it's connecting to the number of charges, which is a macroscopic quantity in UV. So of course here in this all-to-all connected random model, there is no Fermi surface. We are a zero-dimensional problem. But nevertheless, this concept still applies, that you have a relation between your IR and UV physics. And so this goes by the name, again, the general Latinger theorem or Latinger relations. And this gives you actually a relation between these different parameters that I have introduced, deltas and thetas and so on. So the relation is theta f over pi. So you see that on the left-hand side, you have everything that's coming from your low energy stuff that's related to the Green's function that you introduce as a low frequency answers. And on the right-hand side, it relates to the doping value or the charges, right? And similarly, you have the other relation for the bosonic piece. Question?
Hi, I'm a bit confused. So the charge is the global U1 for which the bosons carry. Why is there this Latinger relation on the fermions?
I mean, you have to look at the electron Green's function as a whole, right? I mean, and this electron Green's function is composed of like both the fermions and the bosons. So maybe I didn't quite get your question.
So naively, I mean, in the picture that you drew, where there is no fractionalization, etc., where the electron carries the U1 charge, there is this connection between the U1 charge and the Fermi surface volume, etc. But now, I thought at the mean field level,
so that's yeah, of course, you're perfectly right. I mean, there's an electrical charge, the electromagnetic charge that's carried by the holon.
Yeah.
But of course, you can define any charge. I mean, there is also a charge corresponding to this GF. There is also U1 symmetry.
Right. So is there another?
Exactly. So you can write down for any conserved U1 a corresponding Latinger relation. So there is a U1 that is corresponding to GF, and there's also a U1 that's corresponding to GB, and then you can write down the individual.
So in that sense, the Latinger relation for the boson is sort of the observable U1 and the electronic U1.
I wouldn't
and
say
the
that,
other
because
is
essentially the U1 field that you would write, so let's say when G and B are invariant, right? So so what is essential is that your C is F dagger B, FB dagger. So if you put a charge e power I phi to B, F will have charge exactly e power I phi as well, right? It's the same phi. It's not a different U1. So it's not like U1 cross U1. It's the same U1.
No, but there is a global electronic U1, right? Electronic charge, not this internal gauge here.
Yes. And that, so I cannot write a relation in terms of that global U1 charge. So, but I can write down relations in terms of this internal U1. So that's how you can derive these Latinger relations. So it's so even this U1 is a well-defined conserved thing, right?
Sorry, I'm not understanding. Maybe this is the same question as what Shubhra is asking. So you have two relations, each one of them one involving only fermionic quantities, and one involving some bosonic quantities. That sounds like you have a U1 in which only F transforms and a U1 in only which B transforms.
Yes.
What is such a U1? Because there is no such thing which leaves the dynamics invariant.
They are not different. It's just that you can write two different relations independently. I mean, so you have F going to F e power I phi, and similarly B dagger has to go to B dagger e power minus I phi. So phi is not different for the two. So it's the same U1 field. It's just that you can write down two relations because you can individually look at the Green's function of either the fermion or the boson.
There is another U1 under which F does not transform and the B transforms. Like that's the electronic charge.
Sure, but that's not what we are considering. That's what I'm saying. So these Latinger relations are not derived using that electrical U1 conserved quantity. It's derived using this gauge.
This internal U1.
Yeah.
Maybe I'm being naive, but isn't it true that every U1 gives you one Latinger relation?
Yeah.
So you've written down two.
So in total, I mean, it's basically a single relation. I mean, okay, maybe it's confusing by saying that there are really two different relations. Essentially, you can eliminate P from this equation and you can relate the two equations. So they are not like completely independent. I'm just writing it out in a form that you can relate only the fermionic pieces with the doping and only the bosonic pieces with the doping. But in the end, these two are exactly not independent. You can eliminate P from them and then you have a relation between the bosonic and the fermionic pieces.
You still have two relations, but okay.
I mean, you can eliminate P from this, right? I mean, there's nothing like really independent equations. So you can write this equation in terms of this. And I'll actually show you this is useful because then you get a bound between these parameters theta f's, delta f's in terms of, let's say, parameters theta b and delta b and so on, precisely because you can eliminate P from this equation.
Yeah, but maybe I'm mistaken, but if you keep K and P fixed, and let's say if you change, let's say if you tune J and T.
Sorry, what is fixed?
K and P, you fix it. And if you choose J and T, the way I interpret these Latinger relations is saying that that all this theta B and delta B and so on and so forth will change as I change J and T. But this particular combination will be fixed,
Invariant, yes.
will be invariant,
Right.
even if I kind of tune J and T, right? You know, like because they are kind of fixed by K and P.
K and P, right.
And to the extent that K and P are given,
Right.
they cannot change this combination.
Yeah, but just to pinpoint, that does not mean that you may always have a unique solution. I mean, you could also have multiple solutions that still give you the same K and P, right?
Sure.
Yeah. And it does happen that one of the theta parameters is actually a multi-valued thing as a function of P. So actually you get two values of thetas for the same value of P. But in general, you're right. So if you fix K and P, then your basically parameter space is fixed. Yes.
Yeah. So then you have two constraints, and I'm just trying to understand what is the physics. Usually, you have one conserved charge leads to one Luttinger relation, which gives you such a constraint. But you have two such constraints.
So you can also view like P is the physical constraint in your problem. Right? K is basically just some number that you choose to solve at. I mean, I could have not written this as K. I could have just written it as P over 2, which is the physical value of K. And then essentially I'm just fixing P, right? I'm just fixing one parameter, which is P. I mean, K is a number that was like the control of my theory because I'm working in this large MM prime. But physically the constraint is only on P. I mean, I'm going to fix P.
Yeah, but you still have two constraints, right? What is the, like, how do you derive them? Maybe it's just something I don't understand, but
I don't know. Maybe shall we chat after?
He's saying that you enlarged your parameter space.
Not here.
Hello. Maybe you have enlarged your theory space, your parameter space. Maybe when you set K equal to half that you can connect with the actual original physical system. But in this generalized theory, you do seem to have KP and two independent relations. I think that's probably what Loga was saying. And what are they associated with is this thing that
maybe if it doesn't take too much time, can you maybe spend 1 or 2 minutes just telling how these two relations come about? Maybe that might help me understand.
I can heuristically tell you, but it's slightly detailed calculation. But
just 1 or 2.
Essentially, the idea to derive this relation is again on the same lines as you derive the usual Luttinger relations, where you conserve charge and you have some. You look at the flow of the current corresponding to this charge, and then you write down the Luttinger relation. So even here, it's basically the same. What you are just saying is that maybe it becomes more clear if I write it in this form. So suppose, I mean, these charges are same, but you can derive two different relations because two different Green's functions are related to this same charge. So that's the point. So you have this Q, and you can call some QF, which is related to this GF of tau 0 minus, and you can define some number QB, which is related to your bosonic Green's function, right? I mean, without worrying from where this Green's function or this QF and QB are coming from. This, I can always define some charge QF and QB. And suppose I'm able to write a conserved, and I say that QF and QB are conserved, I can write down a current operator for corresponding to this and write down a Luttinger relation, right? This is precisely what is being done here. It just turns out that QF and QB are not independent. As you can see, QF is P, and QB is precisely 1/2 plus P, or depending on K.
I think the question then is, are they separately conserved, or shouldn't it be the sum that is conserved? I mean, separately, because if it's the same charge, there's no reason to individually conserve them.
No, so you're perfectly right, but it's just that there is a different just a different representation or different way to write the same charge in terms of different parameters. That's the only thing. So for instance, I have a charge in my system, and it just turns out that I have a representation of this charge which is purely in terms of my fermionic Green's function, right? And I can derive an equation using this representation that gives me a Latinger relation. And it just so turns out that I also have a independent or relation which is a representation in terms of my bosonic Green's function. And that's also a perfectly valid starting point, and I can also write down a Latinger relation using that relation.
Right. But in an interacting system, you would think that it's only the sum which is the thing that, so you're kind of imposing that the bosonic charge is fixed and the fermionic charge is fixed.
Yes, and on top of that, they are not independent. That's also the another thing. So as you can see from those two equations, QF and QB are not really independent. Although you derive the two equations saying that QF and QB are independent, but in the end, QF and QB are not independent. And that you can see from that equation and also from this, right? If they were really independent, then there would have been a different parameter P here and a different parameter P here.
But that relative fraction, you have fixed.
Yes.
So that's why you're getting two separate relations. I mean, if I have in this room, I have, I tell you that half of the charges are carried by bosons and the other half is carried by fermions, and I keep that as a fixed constraint, then of course you'll have two separate relations, even though the total charge is, so you're not allowing the charge to fluctuate.
Right.
The individual.
Actually, okay, so maybe this might clarify. So this also comes about because there is also a relation, or there is also a constraint on your fermionic and bosonic Green's function because of like the relation, as I said in the beginning, like F dagger F plus B dagger B is 1, or in this case, generalized thing. So that's another constraint, and probably that probably clarifies thing that you have the questions, that even though you have a charge corresponding to B, your total charge is the same. It's just that you have partition in such a way that your total constraint is always satisfied between F dagger F and B dagger B. So maybe this argument helps, I don't know.
But actually, I had a related question that from your...
Yeah.
Can't hear.
So I had actually a related question that from your saddle point equations, the lambda seems to have dropped out.
That's basically is dictated by the chemical potential. So as you see, I have introduced chemical potentials for F and B's, and they basically depend on lambda. So basically, the way lambda comes about now is you choose mu F and mu B, and lambda is chosen such that mu F and mu B gives you the correct doping that you are looking at.
So is that the other symmetry that you are looking for?
Yeah, I was actually going to ask what happens to QE.
Sorry, what happens to?
QE, the electronic charge. That's also the global U1 that's conserved.
Right. So that's basically again related to QF and QB.
That's what we usually call the Latinger.
Yes, but in this case, you can also write it in terms of like the fractionalized part. But I think that maybe that was the confusion. So you can consider this total charge being separated, like written down as a split between your fermionic contribution and the bosonic contribution, and then write down two independent relations.
But I thought you were putting all the electronic charge on the boson and all the electronic spin on the fermion.
Yes, but you can, I mean, in terms of this U1 symmetry, maybe I'm confusing things.
Two different U1s.
Yeah, exactly.
This
so
is an
global
internal
U1
U1,
I'm not talking about. So I'm talking about this internal U1. Yeah, but I'm not writing a Latinger relation using the global U1 or the charge. So let me again emphasize that. I'm not using that to write down my Latinger relation.
Yeah, so then I think I agree with Rajesh that you are putting further constraints on charge fluctuations to get two different relations.
So that thing I'm not using. The global U1 or the electronic charge, I cannot write down a proper relation or derive a Latinger relation using that.
So is it the non-fluctuation of the charge or the separation of the charge between the?
Important. Yes.
So this has nothing to do with the lambda constraint.
No.
Okay.
No.
Can I just interrupt a little bit? I mean, we just discussed a little while ago what the effective low energy degrees of freedom of your system are. So, I mean, after listening to all this, it seems to me that there is another low energy degree of freedom corresponding to the local U1, like a Nambu-Goldstone type of boson. So there are two low energy degrees of freedom. One is the reparameterization mode, and the other one is the element of the U1 gauge transformation modded out by the global U1. So there are two effective low energy degrees of freedom as opposed to the SYK model. I would think, I mean, just would like to say that to you because of just the symmetry.
That's right. So in this particular model, yes, you're right. So there is also, apart from reparameterization, there is also this U1. That's correct. Yes.
Okay, and then you can write down some effective Lagrangian for both of them and their interactions actually. Which you can write down. Yeah, I understand. Okay, fine. I just wanted to clarify that.
Yeah, no, that's correct. Yeah.
Thanks.
Okay, so then we have these Latinger relations, which basically relates these various parameters that I introduced in the answers in terms of your doping. And as you can imagine, this gives you a handle on now solving the problem because now you have some relations between the different parameters of your theory that you're using. So let me just walk you through how you get the solutions of these equations now directly. Okay, so there are different ways to look at this. So one thing is that keep in mind the ansatz that we have. Now you can also look at what the self-energy looks like when you put this ansatz into the self-energy. And let me just write the form of the self-energies. Now I won't write all the coefficients, but essentially what it looks like is there is a t-square term with some coefficients, and the power here is 1 minus 4 delta B minus 2 delta F. So it just comes about when you insert these answers. There are two GBs and 1 GF, and that's why you have 4 delta B and 2 delta F. And then there is the other term, which is proportional to J square, whose exponent only consists of 3 GFs. So this gives you 1 minus 6 delta F. So that's the self-energy that you have. Oh, sorry, this is not tau, this is omega. And similarly, the fermionic energy, fermionic self-energy has this form. So there's a T square omega Okay, so now you have the expressions for the self-energies in terms of your answers. Now this is the point where you can actually look at what type of solutions or what are the possible solutions in your system. So remember that since we have branch cut and gapless solutions at low frequencies, if you look at G inverse, then this term is irrelevant in comparison to your self-energies, because all the self-energies depends on your Green's functions, and all the Green's functions will have this power, some power set to the power, some exponent. So it's all critical phase. So these exponents will be at low frequencies are dominant compared to this. So essentially, and this is heuristic, but you can also derive it properly by doing the saddle point calculation in terms of or Schwinger-Dyson equations. And essentially the relation is that Gi omega sigma I omega is -1 at this saddle point level. So the product of them has to be -1. So this constraint or this form dictates that for this given ansatz, sigma of z has to go like z to the power 1 minus 2 delta A. So that's the relation, right? So now you basically compare the powers of the sigma that you expect from the Schwinger-Dyson equation and from the powers of the frequencies that you get in the expressions for the self-energy by inserting the answers fully and like looking at the entire expression. And if you now do this comparison, this is how you get the set of solutions I think, can people see this side of the board? Okay. So if you do this comparison, then you get 3 types of solution. The first solution is that delta F equals delta B equals 1/4. Okay, but before that, actually, as soon as you write this relation, you immediately also get a constraint that delta F plus delta B is 1/2. And this is most easily seen if you compare the exponents in the bosonic self-energy. And now you compare the fermionic self-energy, you get 3 types of solution. One solution is delta F is equals to delta B equals 1/4. So you basically equate the exponent from this Schwinger-Dyson form to the J² term. So that gives you this solution, that these have to be equal. And then the other solution is if you equate it to the other one, then depending on that the first term dominates, you get the other solution, which is delta F greater than 1/4, but of course it has to be less than 1/2. And of course the third solution is the limiting one, where you have delta B to be 0 and delta F is 1/2. So these are the 3 solutions of this random TJ model that I have been talking about. So these will describe different critical phases or normal phases of these Schwinger saddle point equations for this model. And perhaps you have already noticed that this is the solution that corresponds to your SYK or SY-like solution. You put delta equals 1/4, the exponent that you get here is square root Z. So this is the usual SYK answers or the Green's function that you get. To be even more clear, what you can look at is the exponents of your physical observables, which are eta S and eta C. So I think I don't need this anymore. So because your Green's function GC of tau is nothing but GF of tau, GB of minus tau, and the spin correlator is GF of tau, GF of minus tau. You can immediately see that eta C, the exponent for the electron correlator, is essentially delta F plus delta B times 2. And because delta F plus delta B is always 1/2, eta C is always 1. So this is always true. The exponent of the electron operator is always 1. Similarly, you can work out the exponent for the spin operator, and this is actually 4 times delta F, simply because you have product of 2 fermionic Green's function. And this now depends on what type of solution you have. So let's look at these different solutions. So for this, when delta F and delta B are 1/4, you get eta S equals 1. So this was the marginal spin-spin correlator that we also talked about yesterday, and this is the type of SYK criticality, right? So the RG solution that I showed you yesterday, the fixed point, the non-trivial fixed point where eta S and eta C both were 1, in this large M parameter space, or this the solution coming from the large M, it corresponds to this one where delta F and delta B are 1/4. So that's the solution. The other solution is also a critical solution. So here, again, eta C is exactly 1. It's Fermi-Liquid-like. But eta S is now, as you can see, it's not a constant. It depends on delta F. So it's a continuously varying exponent, depending on what the value of your exponent of your fermionic piece is, or the bosonic, depends what you choose. And the last one is actually slightly more trivial, because this tells you that eta S is exactly 2. So here again, you have an exact value of eta S, but this is not a critical solution. So if you recall immediately from observation, this is actually a Fermi-Liquid-like. So this gives you spin-spin correlator, which is quadratic in your imaginary time. It's 1/tau squared. So this solution corresponds to a Fermi-Liquid-like phase. Whereas these two solutions are your critical solutions. So both of these solutions are non-Fermi-Liquids, and this one is a Fermi-Liquid solution. So now we have looked at the general model. We have found that there are three possible solutions of this model. Now we actually have to go and see which solution appears at what level or what value of doping. So that's the task. And this task is now like aided by the relations, the Latinger relations, because those relate your doping to the actual parameters of the ansatz that you have introduced in your problem. So now, guided by the solution, you can ask the question, suppose I choose solution 1, you know what the value of delta is, you put back there, and then you solve for a given doping, what's the value of theta f and theta b, and see where the solution is stable. So it turns out, actually, that this 1/4 solution, the SYK-like solution, is confined to a pretty small doping region. So it appears at smaller dopings. It doesn't appear at very large value of doping. Whereas this solution, the other non-Fermi-Liquid, where you have a delta which is varying between 1/4 and 1/2, this is a solution which is actually present everywhere in your parameter space. So this is present all the way to very small doping in the limit p to 0, and all the way to the limit p going to 1. So this is one of the interesting solutions. Now you can ask what happens to the Fermi-Liquid type solution. So this is another tricky business. So it turns out that at least in this large M formulation and solving the saddle point equations in the large M limit, the Fermi-Liquid is actually never a stable solution. And one way to see this is that for this Fermi-Liquid-like solution, essentially what you would have is that your Green's function is not really a critical solution, right? It's a regular function, so it should have a condensation of your holons because this is a Fermi-Liquid. So even though like GF could have some form like this, GB needs to have some regular piece, some condensate piece, which is proportional to your condensation of bosons. And it can, on top of that, it can have some piece like this, which I call GB bar. So it can have some conformal piece, but important thing is that for a Fermi-Liquid, you need this condensate parameter. Only then it makes sense to talk about a Fermi-Liquid. Now it turns out that if you solve your equations, solve this solution using such an ansatz for a Fermi-Liquid, you find that GB of Z or GB of omega goes as 1/omega. And this is a problem because now if you look at, so you have to solve all the equations and you also have to satisfy all the constraints that you get the correct value of doping and doping density and so on. But if you have a form for GB, which is 1/omega, you can immediately see that you get a log divergence when you calculate your boson density, because your boson density is like integral of this GB of omega. So, and that's the reason why there is never, at least in this type of large M theory that I have been showing you, there is no Fermi-Liquid solution. So there are only two possible solutions, and these are only these non-Fermi-Liquids. Okay. So now the task that I will go through in the next few minutes is to actually show you that this second non-Fermi-Liquid solution that we have found actually describes this piece, this novel observation that you have T-linear dependence on resistivity even in a finite range of doping. Yeah.
Sorry, so if I understood right, which delta F is chosen is determined by P.
Yes.
That's what you're telling.
Yeah, or vice versa. So you can also ask the question that these are the three possible solutions, and suppose I choose this delta, then what's the value of P?
Okay.
Okay, so then we have these two solutions, and the argument is that this is the solution that describes this phase, this non-Fermi-Liquid phase with T-linear resistivity in a finite doping region beyond this P star. And the rationale or why this phase could actually be the correct candidate or a good candidate for this observation is again the reason that if you look at the low frequency ansatz or the solution that I'm considering, it's a very general solution. I mean, here when I wrote this solution, it has nothing to, I have not fixed any deltas or thetas. And you can show that this solution essentially has the same time reparameterization symmetry that the SY or SYK type solution has for exactly delta equals 1/4. And the consequence of this is that even for this solution, the resistivity, if you calculate it, has a T linear dependence. So that's the interesting result, that even though you don't have SYK like exponents, you can still have T linear resistivity. And another interesting thing about this solution is this continuously varying exponent or the spin exponent as you dope. Because as you also just pointed out, delta F and P are related. So this dependence on delta F essentially means that your spin exponent is actually doping dependent. So as you go away from the low doping towards slightly higher doping, your eta S is going to change. And in fact, you can, as you can see, if you go to very high and high doping, delta F is going to approach the value of delta equals 1/2, such that it approaches the Fermi-Liquid value of eta S being equals 2. So in the very extreme limit of very large doping, in the limit of P going to 1, you eventually might have a Fermi-Liquid. Although the solution doesn't allow it, but it indicates that there could be a crossover to Fermi-Liquid at some point. So maybe I can just show you some plots. Okay, is this visible? Oh. Mm-hmm. Okay, yeah. So this was the observation that I was showing in the beginning and mentioning now, that you have this finite range. And this solution, the second non-Fermi-Liquid solution, is what we postulate to be a good candidate, an attractive candidate for this phase, where you have a significant non-Fermi-Liquid behavior. So now we basically, I showed you the whole machinery and what are the different solutions. And now we went on and just solved analytically how this solution looks like. So actually for this particular case, when delta is between 1/2 and 1/4, you can analytically calculate the relation between delta and P. So in general, there is a relation, but even for this 1/4 solution, but it's not possible to actually write a closed form relation between the doping and delta. You usually have to solve it numerically to get a relation between the two. But the beauty of this second solution is actually you can write an exact relation between delta and P. It's a complicated relation, but nevertheless, there is a closed form analytic expression for it, which you can, so let me skip this, which you can basically express in this plot. So here, this is, let me first show you the right plot. So this is delta B as a function of P. And this black curve is exactly the one that is the analytic expression or analytic relation between delta B and P, and we have plotted in this plot. And the machinery that goes into getting this relation is again using the Latinger relations, because those are the one that depends on thetas and deltas, and you eliminate certain constants in this particular case, and you get an exact expression. The lower curve is actual numerical data that you obtain by solving fully this saddle point equations at finite temperature. and taking the limit t going to 0. So this black curve is exactly at t equals 0. This red curve with dots is obtained by solving the saddle point equation at finite temperature. So we solve in the Matsubara space, which we can do only at finite temperature. And then we can look at in the low temperature limit, what's the value of delta B. And as you can see, the two agree pretty well. And then on the left plot, this is the corresponding exponent for the spin correlator, which is essentially related to delta B. It's 2 minus 2 delta B or something like this. And what you see here is that as a function of doping, as expected, the spin exponent is changing, and it in fact increases as you increase doping. And only in the limit at very large P, it approaches a Fermi-Liquid like exponent. Yeah.
So in this, so what do you do with your thetas? What is the values you put for thetas?
Yeah, so there are some like complicated values, but you also know what's the exact value of thetas as well in this case. Yes.
Okay, and in the finite temperature exact solution, do you put in the values of thetas?
No. So when you solve the finite temperature saddle point equations, we actually don't even make an answers. We just go ahead and solve brute force the saddle point equations without even telling what type of solution we are looking for. So it's slightly even more unbiased. So we are not even telling it to look for any conformal solution.
And these experiments and so on, you extract from the long time behavior.
Right. Exactly.
Okay.
Yeah. So just to be like, since you are interested, what happens is that suppose you we solve it at finite temperature, and because we want to see if there is any exponent corresponding to it, so you can suppose that you have this conformal solution at t equals 0. You can also generalize this solution at finite temperature, how it looks like. And it turns out that for GB, you have a relation that GB of I omega at the 0 frequency is proportional to t to the power 2 delta B or 2 minus delta B. I might be messing up some factors. So it turns out that it has a temperature dependent exponent, and this exponent is precisely this delta B. So what you can do is you can do this for several different temperatures at very low temperatures, several points, and then do a log-log plot and then try to extract what's the exponent. So this is how these red dots have been calculated by extracting this delta B with fitting such a form of the conformal solution. Okay, so this is what I'm showing here, that the main thing that the spin critical exponent now varies with the doping. And just to show you, we can also calculate the 0 temperature spectral function. So on the left is the electron spectral function. On the right is the imaginary part of the spin correlator. And as you can see, so there are a set of curves for different dopings, and it's color coded here. But the main information that you want to take from here, for example, if you look at chi double prime, you can see that in this blue curve, which is in the very large doping limit, essentially there is almost linear behavior, because the exponent in the Fourier transform chi double prime omega is 1 minus eta. And so, sorry, eta minus 1. So if eta is approaching 2, then you approach a linear curve, and this you see as you go towards higher doping. Whereas at lower doping, you see that there is a very strong power law, because eta is very much away from the value 2. And in the extreme case, when you would have some SYK-like exponent when eta is 1, then in the low frequency limit, it should approach a constant value.
Sorry.
Sorry. Yep. Right. Okay. What is the value of P where you're still in the so-called Fermi-Liquid phase, but you still have T-linear resistivity? Like,
so there is no Fermi-Liquid phase.
There is no Fermi.
Yeah.
Okay.
Exactly. Period. So it's all non-Fermi-Liquid everywhere.
So basically, sort of, if I go back to your original phase diagram that you had shown, you had this Fermi-Liquid on the upper right.
Right.
That really does not come down.
Yeah, at least not in this large M theory. But of course, this is not the true solution, right? I mean, this is, after all, an approximation or a mean field theory in this large M limit. So there are several effects. One is, of course, 1 over M correction and so on. And this will, of course, change the picture. And in reality, you would probably have a Fermi-Liquid indeed, and you should. But at exactly what scale or what doping value there is a crossover from this non-Fermi-Liquid solution to a stable Fermi-Liquid solution, that we cannot predict from these calculations.
And similarly, you also cannot say what happens in the pseudo gap.
I have something to say about that.
Okay.
Yeah, so that is something we can actually say.
Yeah, so I think the chi double prime seems okay, but this I don't understand this spectral weight curve. Is there a dip? Is there a in the blue curve?
Yeah, I mean it looks like a partially like a semicircular kind of thing.
So what is happening? Like so, you have a positive omega, you have something in negative.
Yeah.
Could you explain what is?
The main thing is that there is a discontinuity at omega equals 0, and that's a feature of this conformal solution because you have like spectral asymmetry, and that gives rise to this this discontinuity. And this dip kind of thing that you are observing is actually kind of a reminiscent of, let's say, approaching a Fermi-Liquid, I believe. Because if you were really in a Fermi-Liquid, so if you just take a random hopping model of electrons and ask what's the spectral function of the electrons, then it's actually a semicircular density of states, right? And you see the reminiscent of that when you like approach a Fermi-Liquid limit, you start developing this Fermi-Liquid, semicircular density of states kind of features, but you never quite get there. And but the main difference is that there is really this discontinuity, and that's because you have this asymmetry in your
and could you explain why this? Okay, so you're saying the dip becomes deeper and deeper at larger doping.
Yeah. And eventually, if you really go into the Fermi-Liquid phase, you should like recover a proper semicircular density of states.
Okay, thank you. But do you have any idea of where the dip is? Like, it happens
like
at negative omega.
Value of
yeah.
No.
How,
I mean,
how does
of course we know where it is, but
like how does it scale with?
Yeah, we can have an expression for that, but it's slightly tricky. So what happens is that when you solve these equations analytically, so at t equals 0, you have an analytic handle on this. But it turns out that for this second type of non-Fermi-Liquid solution, you cannot actually fix, you do not know the exact value of these constants that were sitting in front of your answers CF and CB independently. So what you know is what's the product of CF and CB. And that actually determines this. So we actually know what this value is.
But numerically you can determine, right?
Yes.
So because that, if what you're saying is right, that should tell me how the approach towards the Fermi-Liquid happens with doping.
But you don't quite get there. But so that we see definitely, yes.
Okay.
Yeah, and just to contrast this from what the actual numerics on an SU2 system looks like. So I also showed you yesterday that people have done numerical calculation for the SU2 model without doing this large M. And interestingly, they also actually observe doping dependent spin exponent. So let me just walk you through this slowly. So the y-axis is temperature, x-axis is doping. The color code is actually the exponent of the spin correlator, at least in this blue region. So this red region is slightly complicated. Here, if you focus in this blue region, what you see is that this gray line is the one that corresponds to the exponent being 1. So that's the SYK thing. And you see that it goes all the way down to 0. And you have here. On the lower side, you have some spin glass. On the right-hand side, overdoped side, they do call it a Fermi-Liquid. But you see that the exponent is varying continuously as a function of doping. So it's only in the limit where you go to very, very high doping, you start seeing the dark blue color where it actually approaches the value 2. But whereas anywhere in between, it's really a non-Fermi-Liquid kind of behavior. So, so that actually, again, brings back to the point that I think you were asking yesterday. So if you look at just the single particle electron Green's function, then it's really like Fermi-Liquid-like. I mean, even in this solution, you can see that the exponent eta c is still exactly 1. It's Fermi-Liquid like. It's only the spin correlator or the spin exponent that's varying, and that's the hallmark of this non-Fermi-Liquid behavior in this kind of system. So that is really important to what you look at. And I'm not sure, like not many people probably follow the cuprate literature too closely, but okay, unfortunately I don't have this plot, but there have been like interesting RPACE experiments on certain cuprate systems. And what they find is that, of course, RPACE just probes single particle Green's functions and Fermi surfaces. So what they actually find is that they never observe any critical behavior in this RPACE. So they just see some pseudo gap at low doping and like a straight vertical line that divides you from some Fermi-Liquid like behavior. They absolutely don't see any signatures of critical behavior or non-Fermi-Liquid nature. And this is actually related to this thing that we find, that you really can have a situation where the electron Green's function is really just Fermi-Liquid like, but if you don't look at some other observables, you would wrongly conclude that it's a Fermi-Liquid. So that's not the complete story. And it's true that if people have done transport experiments in precisely those regions, and you do find anomalous behavior, although the photo emission just tells you it's Fermi-Liquid.
But no one has tried spin polarized RPACE on.
No, that's, I think, a very difficult experiment. Yeah, that has not been done. Even like measuring the dynamics of the spins, that has been a pretty challenging thing. So if you recall, I showed you yesterday one of the measurements in this strange metal phase where they calculated or measured the density correlator. So I think that's one of the very nice experiments, I would say, and one of the rare examples. Of course, there are a few other experiments that have been done in the strange metal and overdoped region, but I would say they are very handful and very few, especially in strange metal, because it's just very difficult to do experiments in there.
So in a related question, so what is the measurement which would tell us about eta S? You want to do some spin polarized thing, or
no,
would, for example, neutron scattering?
Some spectroscopy.
Would neutron scattering tell you something?
Yeah.
Okay.
But for cuprates, I'm not sure. I'm not an expert how well behaved like neutron scattering is. For quantum magnets, there are localized moments. I think neutrons works pretty well. For cuprates, I'm not sure. I think I vaguely remember someone telling me that I think oxygens are bad for doing neutron scattering on cuprate systems.
Okay.
So one has to devise
some susceptibility, probably magnetic.
Yeah, or I think people do ESR or something like this.
Okay. So you're saying that, so your prediction and these models are telling you that if you do ESR in this highly doped region, you'll see some anomalous behavior. What would you see?
Like the local spin correlation won't be linear in omega, but it would have this precisely some different power law, like what I was showing. So especially near the strange metallic region, you should not see a linear behavior, but some like very strange power laws. So that would be an interesting observation to test this. Okay, so maybe I should wrap up quickly. So since you were asking about what happens at low doping, so what we can show is that this non-Fermi-Liquid phase actually has an instability towards a spin glass phase. So without going into too much detail, is it too much if we can like take the board up? Can we like for a short time take this up and I come back again? Or maybe that's okay. I can just write it here, then you don't have to roll it up. Yeah, so actually, so this is not what I did, but this has been done before me. We just use that technique now here because there is a possibility that this has an instability. So the argument is that you can write down some Ginzburg-Landau kind of functional for a phase transition between a spin glass and either a Fermi-Liquid or non-Fermi-Liquid or something. So basically you can write down a Ginzburg-Landau functional where the order parameter is your spin glass order parameter psi square. And of course there are quartic terms and so on. But the important thing is that just like simple Ginzburg-Landau argument, if this coefficient of this quadratic term is negative, then you are in a spin glass phase. So you have a non-zero psi, so non-zero psi order parameter. If this coefficient is positive, then you are in a non-spin glass or an ordinary phase without any spin glass order parameter. And it turns out this coefficient is actually 1 minus j square over m square times the local susceptibility. Or it might be a square of that. I might be missing some factors. Oh, it's a square. Yeah, so it's j square chi local square over m. So now you can ask the question for this particular model, does it have an instability in towards a spin glass phase by just looking at this simple Ginzburg-Landau kind of argument? It's not extremely precise, but it at least heuristically gives you an estimate whether there could be some spin glass instability. And it turns out it does. So you can calculate the susceptibility in this non-Fermi-Liquid region as a function of frequency. And here what enters is actually only the local piece, so it's only the omega equals 0 part. And you can look at where the sign of this, the coefficient of this changes sign. So can we have the board back? Sorry about that. So this one? Or? Yeah, that's the spin-spin correlator, local spin-spin correlator. So that's chi of I omega equals 0. Yeah, so then you can ask how this coefficient behaves. And these are the plots we numerically calculate for t equals 0. So the left plot is essentially for a fixed value of m, physically m equals 2, and for different values of j. So as you can see, let's concentrate for simplicity on j equals 1. You see that at higher values of doping, this coefficient is positive, precisely saying that there is no spin glass order. Whereas at low doping, at some value of critical doping, it crosses the 0 value and it becomes negative. So this gives you an estimate of the critical value of doping. So this is done at 0 temperature. Similarly, you can also ask the question, what happens as a function of m? So clearly, if you are like strictly in the m equals infinity limit, very large m, there is simply no phase transition. You are always in the non-Fermi-Liquid phase. So as you see from this plot as well, as you increase the values of m, the critical value of doping like goes lower and lower, and essentially for m equals infinity, it would be just not possible. So yeah, this is just for fun that for different values of m, you can have different critical values of doping. And then you can also do this at finite temperature, and this then you have to carefully do the entire numerics at finite temperature, and then you obtain such a phase diagram. So all these red dots are the critical values of doping obtained using such a Ginzburg-Landau criterion. So on the right-hand side at overdoped region, you have this critical non-Fermi-Liquid metal, and then it has an instability to the spin glass phase at low temperature. So this is the temperature versus doping. And it kind of looks nice in the sense that at least phenomenologically, it looks like the cuprates that you have at low doping, some spin glass, whose order parameter vanishes like as you increase doping, and then it goes into this critical non-Fermi-Liquid where you would have key linear resistivity. Of course, the shortcoming of the present model is that it doesn't take you all the way to the Fermi-Liquid, but then with appropriate corrections, we believe that eventually this has to become a Fermi-Liquid. So yeah, that's the story where I would like to end.
Sorry, what numerics are these?
Essentially just solving the saddle point equations at finite temperature in the Matsubara space.
So why is it, I mean, I thought that in your previous sort of plots or also yesterday, P around 0.2 was, so is it because of this being not m equal to 2 and a different?
You mean which
I thought that the critical point was around 0.2 or something.
Here?
No.
In the numerics and all. Yeah, but that is like exact numerics at m equals 2, right?
Okay,
I mean,
so this
was
is not
like a saddle point equations that we have in the large m.
Large
limit,
m, okay.
But then by hand we are putting m equals 2, so
okay.
it's a very drastic approximation. But nevertheless, it gives you some estimate for the doping, and it's not completely unreasonable. I mean, it's like around 0.3, which is okay. And okay, one more interesting thing is that it's also corroborates with the PC that you get from RG. It was roughly 1/3, but that's putting too much faith and too much optimism into it. But yeah, independent of that RG, you get some finite critical doping. Yeah, okay. So this is the story, and I would like to end with this. Thank you.
Okay, yeah, thanks for the very nice talk. Let's and we have time for a few more questions.
What is the spinless order parameter in terms of the underlying? What is the spinless order parameter in terms of this B and F?
Yeah, good question. So this, that I cannot write down a very easy expression for that. But essentially, what you have to do is the whole thing that I derived for the saddle point equations, you have to carefully do it with keeping all the replica of diagonal terms as well. And it turns out that the bosonic Green's function would have the zero frequency component of the bosonic Green's function when you do this in the spin glass phase would have a component which corresponds to this, which has this psi contribution, and then there would be some other pieces as well. So this is roughly related to like the zero frequency boson Green's function. But I should point out that this boson Green's function itself doesn't have this conformal form. I mean, it has this form that you have this condensate and then some regular piece which may have some conformal form, but we don't know.
Okay.
This psi is real. This order parameter is real.
Yes, it's real. Yeah. So there the bosonic, so there you have to actually use the different representation. It's not the same representation. So there you have to make the holons to be fermionic and the spin-ons to be bosonic. Yes. Yeah, that's also crucial. So it's not the same GB, it's different where you have switched now.
Okay. Any more questions?
So about this Fermi-Liquid phase is instable when you're saying, you said something like this bosons cannot be, you cannot condense the bosons, right? What is the argument like
so it's actually exactly, simple in the sense that you do it by contradiction. So you assume, let's say you can condense the bosons. That is what you would expect for a Fermi-Liquid. So then you say that your GB is of the form that there is some condensate and then there is some regular piece. So you can solve this and you can solve the solution and you can get some solution by solving just the Green's function and the self-energy. And then the solution that you get, the frequency dependence of this GB is like 1 over omega. But of course, this you have not solved the set of equations or the family of equations completely, and you cannot say that you have the final solution unless you satisfy all the equations and make sure that your doping value that you get is exactly consistent with the solution that you get. And that's where this fails, that if you now calculate what's the boson density for such a solution, you see that it has a log divergence with omega. So it doesn't have any finite value. So that's the problem. So finding a solution with this condensate is not a problem. It's just that this solution is not correct because it gives a diverging boson density.
Okay. So if there are no further questions, let's thank Darshan once more.
Thank you.